Okay, so today we're covering chapter 11.4, 11.5, and 11.6, which is graphical interpretation. Graphical interpretation is pretty important in the fact that we are constantly trying to improve what we're trying to tell people through our graphs, understanding what our axes mean, why it's so important that we use and tell someone what the axis is, along with a symbol to be used in any equations, along with anything else that needs to be included in your graph. And so for graph interpretation, we use things to convey information. So talking about the area under the curve or the slope of the line, the shape of the line. So those all tell us something about what that data represents or means. And so talking in calculus terms, so you can differentiate to get your area under the curve, slope of the line. You're going to integrate things, so you can use differentiation and integration to understand exactly what is happening. In this case, for this course, we don't get into that because you may not see those concepts quite yet in math if you are just now taking Calculus 1. And so understanding what is a derivation or what is an integral mean in terms of you can go from distance to velocity to acceleration, or acceleration velocity to distance, depending on whether you're integrating or you're differentiating. But in the case of the area under the curve, it's really just formatting or calculating that area using basic shapes. Our slope of the line, we usually use, rise over run. So y2 minus y1 over x2 minus x1 to calculate what is our slope of the line. So going back to some simplistic math terms in that format. And so here we've got a graph, this red line. So we've got kind of a flat line at 25 watts for 15 seconds. Then it completely drops off to 0 watts after 15 seconds. And so we're looking at our two axes, our abscissa, or our x-axis being time in t units of seconds, and then our ordinate axis or y-axis being power p in units of watts. So these things are important in the fact that so we can look at what do these things mean. And so if we're looking at the slope of the line, we have power divided by time. If we look at area under the curve, we're looking at our power multiplied by time. So which one gets us to a quantity that we understand?
Could you repeat the question, Professor?
Yeah, so if we're looking at area under the curve, we have power multiplied by time, right? So we've got just a box under our curve here, and our curve is really just a bunch of straight lines. Or if we have our slope of our line, we're looking at power divided by time. Which one gets us to a quantity we understand or have covered in class? And what would that quantity be?
Power multiplied by time.
So if we do power divided by time, watts divided by seconds, what is that?
That's just energy.
What is it?
I meant P times T equals
Power
heat.
times time gets us to energy. So power, remembering watts, can be worked out as joules per second. And that joules per second multiplied by seconds gives us just joules in the end. Okay. So we take those two axes, calculate our area under our curve by multiplying the two. So if we have 25 watts times 15 seconds, what is our total energy according to this curve?
$375.
75.
375. And what are our units?
Joules.
Joules. Okay. And so if we have this second graph, now we've got a graph that includes a slope. We've got a linear line that goes from 0 to approximately 375 over a time of 15 seconds, and then it flatlines at 375 watts. Now our axis is energy for our ordinate axis in joules. So now, how do we calculate power?
Energy divided by time.
So our energy divided by time, which is now our slope of our line, is now telling us how much power output we are getting from our graph. So we can take that, energy and time, divide the two. So here we already did this one. So our 25 watt light bulb is turned on and turned off after 15 seconds. We know that that has an output of 375 joules. But now we've got a graph that has a linear slope to about 3 seconds. It flat lines at 25 watts until 10 seconds, and then from 10 to 15 seconds it decreases linearly back down to 0. So what is the total energy from this graph? And how might we calculate that?
The area under the curve.
We're going to calculate the area under the curve, and how do we represent these different areas under the curve? So for triangles, we get our base times our height divided by 2, and then our area for a square being our base times our height. So if we break this down, we've got triangle 1, we've got 1 square, and triangle 2 that we can calculate based on our axes. So go ahead and take 2 minutes and calculate the total energy outputted by this light bulb. Okay, so looking at the median line shapes, up until this point, we have worked with just linear lines in our examples. And our linear lines do tell us quite a bit. So if we're looking at a horizontal line, we know that our variable is not changing, meaning that the slope or the derivative is 0, and the area under the curve or the integral is increasing at a constant rate. If we have a vertical line, we know that the variable is changed instantaneously, the slope or derivative is undefined or infinite, and the area under the curve is undefined or 0 when it does that instantaneous jump down or up, depending on which direction it is moving. And then for our straight line, a positive or negative slope, which is neither horizontal nor vertical, so linear positively or linear negatively, slope rate. So our variable is changing at a constant rate. So the slope or the derivative is constant and non-zero. Then our area under the line is increasing If the slope is positive, the rate of increase is increasing. If the slope is negative, that rate of increase is decreasing. And then if the negative slope line goes below 0, your area will then begin to decrease. And so in one of these examples, we will work through, or even in your homework, you're going to have examples. And you're going to notice that not a single one of the graphs that we produce here actually goes below our 0. So our area under the curve will never begin to decrease. Then we have our curved lines. There are 4 types of curved lines. So our curved line concave up, which is an increasing trend. Our curved line concave down, an increasing trend. Our concave up curved line with a decreasing trend. And then our curved line concave down with a decreasing trend. So each of these either has an increasing rate or a decreasing rate, depending on what our variable is doing. And then the slope of the curve or the derivative is positive and increasing for our first 2, our increasing trend lines, whereas the slope of the curve or derivative is negative with a decreasing magnitude for our decreasing trends. And then your area under the curve is increasing in all of these at different rates, either an increasing rate or a decreasing rate, depending on what direction it is, a positive or a negative slope, okay? So if we bring up an example here, and so I've provided a graph that has velocity and time on our axes. We're going to use this chart of 0 for number 1, positive and constant for number 2, positive and increasing for 3, positive and decreasing 4, negative and constant 5, negative with increasing magnitude 6, negative with decreasing magnitude 7 or 8 cannot be determined from the information given to describe what is happening in this graph. So if we look at between points A and B, the acceleration is what in 1 through 8?
Constant.
So it's constant, so it's either, so that narrows it down. Is it positive and constant or negative and constant? So number 2 or number 5? So it's number 2, positive and constant, because we have a positive slope on our linear line. And we say it's constant because we know that a linear line, it has a constant acceleration, acceleration being our slope of our line, right? What would be the area under the curve at this point?
Six joules. Oh, it's velocity, but 6.
So we've got velocity and time. So 6 is what? What are the units on 6 when we calculate this?
Meters.
So meters, so that tells us that we are traveling what? What does meters represent?
A distance.
Like a distance, a length of something, right? And then between points B and C, what is our acceleration? How would we describe that? 1 through 8.
Zero.
0. I'm seeing a lot of 1s pop up in the chat. Great. So now between points C and D, what is our acceleration? Seeing a lot of 5s, so negative and constant. Are we going forwards or backwards? So we are, even though our acceleration is decelerating, we are still moving forward because we are still adding to the distance that our car, if this was a car, is going. Okay. So now between points E and F, your distance is what? Saw a couple of ones, but we kind of rethought that. So we're describing our distance first, then we can calculate. Between E and F, when we calculated it, it's 4 meters, but how do we describe this in 1 through 8? So we're 0, positive and constant, positive and increasing, positive and decreasing, negative. Which one of those describes this? So I've got 2 right answers. 3 positive and increasing, because so far we've gone X number of meters in distance. And now we're adding to that, and it's still a positive number. We have not gone below our x-axis or our 0 axis to start subtracting from our distance. Between points F and G, what is the distance? How would we describe it? Still 3, right? We're still positive and increasing. At this point now, we're increasing at an increasing trend. And G and H. So our distance is what?
Increasing. Oh.
It's still increasing. But distance is calculated by doing what? Is it the slope of the line or the area under the curve?
Area under the curve.
Area under the curve. So we aren't worried about the slope. While we have a negative slope for this, we are still adding to the distance we've traveled. So we're still positive and we're still increasing, but at a decreasing trend. So understand how your area under the curve changes versus what is your slope telling you. So lastly, just a little bit on other ways that you can use graphical solutions to tell data. So in the business world, which engineers need to kind of pay attention to, because if you are ever producing a product or manufacturing something or working where you are selling products of any kind, which most of the time you will be, you are going to have to do a break-even analysis. So even if you come up with a brand new product, how long is it going to take you to break even if you are selling your product at a constant rate? Or how many products do you even need to sell in order to break even, okay? And so we can graphically represent this, doing a cost analysis of our product being produced and looking at the revenue from selling that product to assess our profitability. And so your cost has two different types of cost. Your fixed cost, which is your startup cost, what it costs to invest in a building or your starting equipment, whatever you need to produce your product. And then you also have your variable cost, which is your day-to-day cost of your manufacturing process. So how much labor, energy, or material. So if you look at this over weeks, and say you don't work Friday, Saturday, Sunday, you're obviously not going to have costs other than energy costs over those days. So your variable costs may change from day to day, but over weeks it will probably even out and give you a line that you can work with. Then your revenue is the money made by selling your product, or the selling price. And then if we're looking at our loss, that's before we break even. Our profit is after we break even. And our break even point is where our cost and revenue lines intersect. So given an example, and this is a very simple example because not everything is going to be nice and linear. But if we have our total cost line and it starts, that is the red solid line, you're going to see that the slope of that line is less than the green dashed line on there, which is our revenue line. And our revenue line will always start at 0, 0. Whereas our cost line will always start where we have our fixed cost for our startup. And so that fixed cost is what it costs to put in, buy a building, rent the building, things like that, whatever equipment you need to start. Then your variable cost is the slope of your cost line, so your day-to-day costs over time. Then our selling price is the slope of our revenue line, so that dictates. And then our break-even point is where these two lines intersect. And so anything before that is a loss, meaning that we are still in the red and haven't made a profit yet. Once we hit that break-even point, everything turns black in our ledger and we start to make money off of whatever we are selling. So here we usually do a break-even analysis in the number of units that need to be sold, because you don't necessarily know that you will sell X number of units per day. You could eventually put a timeline to this and, you know, chart how many products you've sold over time. But your cost or revenue are both on your y-axis, so really that's your money. So here, for an example, we produce fire ant destroyers, which it is springtime and the fire ants are starting to come out again. So these are definitely needed. And so if we have our company and we are producing and selling fire ant destroyers, our total cost line is our solid black line. Our dotted orange line is our revenue line. How many of these must the company produce and sell to break even?
$1.7 times 10 to the fifth.
So we are at 1.7, or 170,000 units need to be sold in order to make a profit or start making a profit off of these fire ant destroyers based on the selling price that we have set and our daily costs that we incur. So now we want to make a profit of $500,000. How many units do we need to sell in order to make $500,000? So how do we determine what our profit is, or how much of a profit there is?
We look at the orange line.
So our orange line is our selling price minus our cost line will help us determine where our revenue is. So obviously, if your cost line is above your revenue line, you are losing money. If your revenue line is above your cost line, then you're making money. So we are looking at where that difference is 5 little squares, which indicates $500,000, which occurs at 260,000 units. So based on our graph, what is our sales price of one fire ant destroyer? So we know the selling price. What are we looking at?
Total cost minus the revenue at 0.1.
So we're looking at what the sales price of our fire ant destroyer is. So we are looking at the slope of our revenue line tells us what our selling price is. So what is the slope of that orange dotted line? 10 what? So numbers are handy, but numbers don't tell you anything unless they have units with them. So what are the units on our coordinate axis or our y-axis?
Dollars.
Dollars.
So dollars in the millionth, right?
Yeah.
And then what is our abscissa axis?
Number of units.
So number of units. So we're looking at $10 per unit is what our sales price is of our fire ant destroyer. So if we take this and increase our price by $1, how many units must the company produce and sell to break even? So we have our current revenue line. Now we've upped that and increased our revenue line to now hopefully create a new break-even point by increasing the sales price of our fire ant destroyer. So when are we going to now break even?
140,000.
So at 140,000 units, what happens if we go in the other direction and decrease it by $1? So now it's $9 per unit instead of $10 per unit.
$210,000.
So we're looking at 210,000 units. So when you are looking at pricing a product, being able to do this type of analysis very generally to kind of give an idea is really important to understand how many units do you need to sell. And based on that, are you selling these to? What should you price them at? What's fair versus what will get you to where you need to be to break even. And this can definitely get complicated because say you are a massive company producing toilet paper right now, right? And in order to meet demand of toilet paper in the country, you may have facilities you've got to flip over that produce different products to now produce toilet paper because there's a larger demand for personal toilet paper products than there are for commercial toilet paper products. And so understanding how that cost line will jump when you've got to convert equipment over is really important. And it is definitely something that you should know how to do if you are ever going to get into being an entrepreneur and producing your own products, being able to do a break-even analysis to at least generally understand where you will be. Okay, so that's pretty much all I have for today. I have a quick quiz for you guys to do and then an exit ticket for you to do. Obviously, I'm way under on time. What I ideally would love to do for the next class period is if you guys can go out and find a graph that you may be confused about reading, or a graph that you are having a hard time understanding, and upload that for extra credit so that I have it, so I can put together and go over some graph interpretation and what are some bad features of a graph versus a good feature of a graph. Oh, Joanne, you're muted. Okay.
Yeah, I have a question. All these extra credit opportunities, they'll each have their own separate link to upload, right? Okay.
Yep. Yeah, you get up to 4.